Hello everyone, in this video we're going to go over section 9.3 and the addition rule. So what is the addition rule? If you have a set A that can be seen as the union of mutually disjoint subsets, like a collection of subset A1, A2 up to AK that are mutually disjoint, so intersection is empty, then you can kind of see the number of elements in the set as the sum of the elements in each of the sets of the partition, the mutually disjoint partition. So the subsets share no elements. If they overlap, you cannot simply add up their sizes. You need to at least subtract the intersection one. So that's why it's key that these are mutually disjoint sets. They have no intersection between two sets. Now, the strategy here is that you partition the set you want to count into these joint pieces that are individually easier to count, and then you're going to add. So an example of that. Let's consider the 3-digit integers that are divisible by 5. So integers divisible by 5, they're going to end up on 0 or 5. So for example, 15, 25, 35, they end in 5. And 10, 20, 30, they end at 0. So we have two cases. Case A1, where the 3-digit integers ended in 0, and A2, the integers ended in 5. Since these are clearly disjoint, they can end in 0 or 5, but not both at the same time. Now, for any of A1, remember, we're counting 3-digit integers. So the first digit, which is the 100, can only vary from 1 to 9, since we're not going to have 0 at the start. If we have 0 at the start, it won't be really a 3-digit integer. So we can only have 1 to 9. So we have 9 options. So for the 10th digit, we have 10, because now it can be 0 to 9. So we have 10 options. And the units can only be 0. So in this case, we have 9 by 10. So it's going to be a total of 90 possible 10 3-digit integers divisible by 5 that end up in 0. Same reasoning for the integers that end up in 5. Is going to be the same amount of numbers. The only thing is that the variation is going to be at the end, where the units can only be 5. That is a fix, but the other ones are the ones that are varying. So that's going to be 9 by 10 anyway. It's going to be 90 again. So the total number of 3 digits divisible by 0 or 5 are going to be 180. Now let's talk about the difference rule. So the difference rule is if you have a finite set and that finite set B is a subset of A, then we have that the number of elements on A minus B can be seen as the number of elements in A minus the number of elements in B. In particular, this is going to be something that makes sense because A is a finite set. So we're pretty much subtracting numbers. If this is an infinite, it doesn't really matter if B is a finite or not. It just matters because A is finite, then B is going to be finite, and then this is going to be numbers that we can subtract. Okay, so now one of the reasons why this works is because B and A minus B are disjoint. You can kind of see A as the union of B and A minus B. So by the addition rule, this is going to be the number of elements in B plus the number of elements in A minus B is equals the number of elements in A. Then we're just going to move this number of elements of A to the other side, and we get the formula that we got. In general, this is going to be good for counting by complement. When it's hard to count what you want, you count what you don't want, and then subtract from the total. So it becomes a thing of the number of things that I want is the number of things in the total minus the number of things that I don't want. So one example of this would be, let's go back to the example of the 4-digit pens. So we have 4 symbol pens from 36 symbols. The total number of pens is going to be 36 to the 4, allowing repetition. And the pens with no repeated symbol is going to be the permutation of 36 with 4. Which is going to be 1,000,000 for 400,000 and 30,720. And then now, if we want the pens with at least one repeated symbol, that's pretty much the subtraction between these two. So that will be from the total subtracting the non-repeated symbols. So if I'm subtracting those, the option that I'm gonna get is that they have at least one repeated symbol. They might have more, but they have at least one more. So I get that that is 265, 896. And so I can calculate the probability of having at least one repeated symbol by just doing that event over the total, which is going to amount in this case to 15.8%. Now let's talk about the complement formula. So if S is a finite sample space and A is an event in S, then the probability of the complement is 1 minus the probability of the event A. This is because a complement can be seen as the sample space minus the set A, or the event A. And then, of course, when I use the formula for the probability, which is counting the amount of things that we have in here, it's going to give me the probability of the sample space minus the probability of A, and the probability of the sample space is just 1. So the duration of this difference rules, once again, is given here. The probability of the complement is the number of elements in the sample space minus the number of elements in A over the number of elements in the sample space. And so at the end, I can just rewrite this, put n of s in each of the fractions. It's just going to give me 1 minus n of A over n of s, which is just 1 minus the probability of A. Now, if we apply that to the pen example, for example, we can use the probability of having no repetition being 0.842. So the probability of at least one repetition will be 1 minus 0.842, which is going to give me the 15.8%, which is exactly the amount that we got before. So this is a second way of getting that particular result. Okay, so now let's talk about inclusion-exclusion. So when two sets are overlapping, notice that before we were talking about sets that they were disjoint, but now we're going to talk about sets that overlap or events that overlap. So for any finite sets, if A and B are sets that overlap, then the number of elements, the union of A and B, is going to be the number of elements in A plus the number of elements in B minus the number of elements in the intersection. And of course, this inclusion-exclusion for two sets can be expanded to multiple sets. In particular, we can do it with 3 sets. The number of elements in the union of A, B, C is going to be the number of elements in A plus B plus C, minus each of the intersections, minus the number of the intersection of A inter B, minus the number of intersection of A inter C, minus the number of intersection in B inter C, but plus the number of the intersection of A inter B inter C. The reason why this happened is because this is when we are getting the subtractions, this intersection, when we're counting here the number of A, the number of B, number of C, we're counting at least the intersection 3 times, right? And so the number of intersection is 3 times here, but we're subtracting the intersection 3 times here. So we need to add at least one of the intersections to keep it. And so that's why we keep the intersection between A, B, and C. So the intersection between all of them is counted at least once. This is something that you can easily see if you're shading the Venn diagrams. So I encourage you to try reconciling this formula by doing Venn diagrams. One example of this would be in a class of 40 students, 18 play soccer, 15 play basketball, and 17 play boat. So let's say the number of students playing soccer or basketball will be 18 plus 15 minus 7, because it will be the number of students playing soccer, which is n of A, the number of students playing basketball, which is 15, and 7 that are playing both. So we subtract the intersection, so we get that. It's going to give me 26. We can go with calculation like, well, what is the probability that I at least play one of those? And one of those is either soccer or basketball. So that's going to give me 26 out of 40 that are in the total. And then we get a probability of the 65%. All right, so in summary, we learned about the addition rule, which is that pretty much the counting, the union of disjoint set is just going to be the sum of the number of elements in each of the disjoint sets. We learned the inclusion exclusion, which is that when we don't have disjoint sets, then we gotta subtract sometimes the intersections. So the number of elements in A union B is going to be the number of elements in A plus the number of elements in B minus at least one time the intersection, since every time when we count the elements in A and the elements in B, we're counting the intersection twice. So we need to remove at least one of the intersections so it does not count it twice. Okay, the difference rule was something that we also learned, and is that when we have finite sets A and B, then the difference, the number of elements between A minus B can be calculated as the number of elements in A minus the number of elements in B. The complement formula is the probability of a complement is 1 minus probability of the event. And we can use it to count by complement, counting the opposite and subtracting from the total. Now, some common mistakes that happen here is that you do count overlapping sets. So the addition rule requires that the sets are disjoint. And if the sets overlap, then the intersection will be counted twice. You gotta be careful with the different rules if B is not a subset of A. Always you need to confirm that B is a subset of A first, otherwise you cannot just use it. And forget to define the set clearly. When you're using the complement, you need to be explicit about what the sample space is.